Hello, I'm Verdi Arbusto. This is the Schumann Resonance Harmonics channel on YouTube and on Facebook. Thank you for being here. It is the 25th of January. It is Monday, if I remember correctly. And this is part 3 in the video giving detailed explanation about the Schumann resonance antennas. This is part 3 of the, let me adjust my camera here. Okay, that's better. This is part 3 of the video series where I introduce the Schumann resonance antennas. The article that I'm going by is called A New Portable ELF Schumann Resonance Receiver, Design and Detailed Analysis of the Antenna and the Analog Front End by Constantinos Votis. From the, and this was an article that was published in EURA SIP, Journal on Wireless Communications and Networking in 2018. Okay, so that's the, that's where I'm getting this from. I'm just going to get right into this. This is a video on the magnetic induction coils of the Schumann resonance detector antennas. The first video, I went into the abstract, which is just the concentrated introduction. The last video, I went into the introduction, which is a longer, the longer basic part to this. And this part here, I'm just going to get into. This is the magnetic induction coil. So there's the 3 parts of this. Okay, all right, enough stalling. I got to get on with the material. All right, so this is technical kind of stuff. I just want you to know, and this may not be the most fun stuff to have to go through. Okay, I get that. However, relative to learning about the Schumann resonances and the electromagnetic radiation in the environment, unless a person understands how the antennas are made, how they are configured, and the limitations of them, you will never understand what the spikes mean. Right? The spikes are electric, and the spikes are the fantastic, the fabulous part of the Schumann resonances that everyone loves focusing on. They're the dramatic, they're the spectacular, the amplitude spikes are, yeah, we're moving, we're going. So, everyone loves to focus on the amplitude spikes when those are only momentary, and those are not the Schumann resonances properly. Schumann resonances are what develop over the course of time. And this could be days to weeks we're talking about. Amplitude spikes are momentary, they are electric, they're sharp, they're quick, they're fast, and they do what they do. The bigger part of They do what they do, but it's quick. The bigger part of the effect of the Schumann resonances is the magnetic portion, which stays around a lot longer than the electric side of the signal. Once it goes out, once the amplitude signal goes out, it starts converting immediately into magnetics. It sticks around for a little while until it transfers or transmutes into the electric side. It's like gravity pulls it down. That's sort of a way to look at it. There's a consistent gravity that pulls the height of the amplitude down into the ground, into earth ground as I call it. Okay, so what we're going to be looking at here is the magnetic induction coil. I have this up on the screen already. This is the first, in my view, this is the first most important thing that a person should learn about the Schumann resonance antennas is the making of the induction coil. Without a good coil, you can't get a good signal. It's that simple. So because we are learning about the Schumann resonances, and as I have said before, I've said this multiple times, if you don't know how the antenna is made, if you don't know how the antenna is configured, then you don't know what you're looking at on the scope, because the scope is not abstract art. It's not gotten in there with some scientist who's playing with the colors and, hey, this looks groovy. The spectrogram and the scope readings are all a result of an antenna signal that gets processed and sent through the works. This is extremely important to remember, that anything that you see on the spectrogram is a result of a meter reading and a printout from one of these. Okay, if it's the electric, it's amplitude, and that is one measurement. The horizontal is the magnetics, and that's another measurement. They're two different machines that get sent into the same end machine, which tabulates both of them. This is the spectrogram. So at the end of the spectrogram, you have the amplitude and the magnetics, which get put together to form a cohesive picture. But there are two parts to this. The more important, again, relative to the Schumann resonances, the more important part of this is the magnetics. There's a lot of mumbo-jumbo, a lot of hoodoo-guru about what the amplitude spikes mean in the religion of Schumannism. All right, people get all worked up. Oh, there's nothing going on when there's no amplitude spikes. There's a lot going on. You just don't know what you're reading. So that we don't have to keep going through there's nothing going on, and so that you understand what you're looking at. When you're looking at the Schumann resonance charts, we're doing this. You need to understand how the antennas work, because without understanding how the antennas work, you don't know what you're looking at. It's that simple. All right, so I would like you to understand what you're looking at when you look at the graphs for the Schumann resonances. It's really important to know what you're looking at when you're looking at these things. Okay, so I've repeated myself ad nauseum in this, but it's extremely important that I make this point, that without understanding physically how they're getting the signal and then processing it and what it takes to get that signal, there's a lot of witchcraft, witchery that comes with the technical scrying and trying to transliterate what the Schumann resonance spectrograms mean. So we are going to be looking at the magnetic, and so that is why, and that is wherefore we're doing this, and we're going to be looking at the Schumann resonance magnetic antennas, which are the induction coils. Okay, so the literature here, let me get myself out of the picture. Okay. All right, so this is magnetic induction coil, as it says. Experimental measurements on Schumann resonance field magnetic components involve antenna implementations that are usually inductive coils with efficient magnetic properties and enhanced detection sensitivity. Ferromagnetic core exhibits a relative magnetic permeability of the order of 10 to the 5th, providing high induced voltage amplitude. Mumetal is a soft ferromagnetic material that exhibits a maximum magnetic permeability of the order of 2 times 10 to the 5th. Our antenna implementation is based on induction coil architecture with Mumetal, that's right here, Mumetal, M-U-M-E-T-A-L, core material. M-U-M-E-T-A-L. The Mumetal material, which has a catalog number of ASTM A753 Alloy 4, exhibits very small coercive force, very low core loss, and remanence. I'm not sure what remanence is. Due to the fact that our core is a rod that is open-ended, the resultant equivalent magnetic permeability is much smaller than the Mumetal relative magnetic permeability, and is given in equations 1, which is below. 1 and 2. Okay. Also, It strongly depends on the relative permeability of the core material as well as the induction coil geometry through demagnetization, oh my God, through demagnetization factor N. Equations 1 and 2 give demagnetization factor N and the resultant magnetic permeability, which is the mu number, of an induction coil. Okay. All right, and so what they're doing is they're showing us, come on. Okay, so they're showing us this equation here, and I'm not, hold on, hold please, system processing, let me find myself here. Come on, where are you? There we go, okay, I'm trying to find myself, there I am, all right. Sorry about that. I have two screens I'm trying to work on, and it's either on this one or that one. All right, so so this equation, I'm not a math guy. I can't tell you how to figure this out. This is their coefficient for how they're figuring out the magnetic permeability of the material that they're using. Okay, so that's equation 1. That's equation 2. Okay, again, I don't know how to read this, but they're explaining a little bit more how they do this. Okay, all right. So where m is the length to diameter core ratio, m equals 300 over 25, which equals 12 in this research, and mu r is the relative magnetic permeability of the core material. In this work, n equals 0.0151. Okay, so they have already kind of figured out what their values are of the material. In practice, choosing a quite large induction coil length is a benefit due to the resultant high magnetic permeability, reference 23. But taking into account that as the length of the induction coil increases, the ratio m also increases, eliminating the demagnetization factor, value n, as observed from equation 1. That yields to the fact that the resultant magnetic permeability, mu, exhibits quite strong dependence on relative magnetic permeability, mu r, of the core material to equation 2. Okay. And again, I have all this, where am I? Okay, so again, I have all this over on the right-hand side, so you can read it maybe a little bit better. I'm going to be posting the Word document on the right-hand side into the WordPress blog, so you can read it and that you're able to digest it and it makes it sense. Okay, and it took a little while to kind of break all of that up, just so you know. But I'm doing it for you because you're wonderful and you deserve it. Okay. Moreover, the value of mu r presents crucial instability from temperature or applied field frequency variations. Therefore, the induction coil sensor performance may be crucially affected and degraded through variations of magnetic permeability mu, or variable mu. As that material presents high relative magnetic permeability, equation 2 is modified to equation 3, and the induction coil magnetic permeability depends on the value of demagnetization factor N. Okay? And this is what it's telling you. They have, how do I say this? That second equation, the second equation is basically a readdressing, it's a refining with a length change, if I understand this correctly, a length change in the coil, so they re-evaluated the N, which is the magnetic permeability index, if we'll say, or it's the variable at any rate. Okay. Figure 1, which is below, depicts a block diagram of the single induction coil, and Table 1 summarizes the corresponding geometry values. The windings should be laid on the core within 70 to 90% of its total surface in order to take advantage of the maximum possible flux. Okay, so this is really important. I'm going to read this again. The windings should be laid on the core within 70 to 90% of its total surface in order to take advantage of the maximum possible flux. Okay? All right, and I am going to this. All right, I think we can kind of see that. All right, I'm just kind of putting this in so we can all see it. All right. I want to be able to see this all. I want to be able to see this all in one screen. So that's why I'm kind of fiddling with this. All right. Okay, so what we're looking at, this here, the I, this is the length of the core, a total, okay. You have the D total is, they're giving all these values here, and this is the height of, this D total is the height of the windings and the core. This D core is the length, the diameter of the core itself, and then you have the T are the turnings, or the windings, they also call those. Single induction coil geometry. Our induction coil, our induction coil architecture is depicted in such block diagram. The core Mumetal material length, and that's L core, and the diameter, D core, as well as the length of the copper windings, L winding, are also shown. We implement that induction coil antenna using copper wire, diameter -D wire, and making end turns of windings that cover 70 to 90% of the total core length. The total induction coil diameter is defined by the thickness of windings T and the core diameter D core, D subcore, providing that the total number of turns should approximate to 40,000. Okay. So this is something that they talk about. This is something that they regularly talk about, is the amount of windings that are in any one of these given coils. Okay. And there is a value. It's really important to understand that because of what the fields are, the magnetic fields are, and the variance of the signals that are in there, you need to engineer the turnings. You need to engineer these magnetic induction coils to the frequency. You have to tune them to the frequencies that you're looking at based on the type of wire, the purity of the wire, the size of it, right? There's different qualities of wire. It's not just copper, okay? You want pure oxygen-free copper. That's the first most important thing. You want it of a certain diameter, certain thickness. You want a certain length of it, of the overall length, which gets turned into windings on your coil. So essentially, that wire does get turned into a coil, but it's on the former, the core of the magnetic induction coil. So the windings, they're telling you these here go to 40,000. Okay, they're stopping at 40,000. When there are other antenna makers who go up to 100,000 windings. And depending on the type of signal, the range, the frequency range you're looking at, you have either the 40,000 or the 100,000 of a smaller wire. There's a lot of variables that go into the proper selection of the wires for these antennas. It's not like just a piece of copper they put down. There are windings, and you see the equations that they go to figure these things out. they're approximations of the values, but they need to have, right? The equations are just approximations with the variables, and they just want to give a range. It's not as exact as people would like to think it is, even though it deals with numbers. And so there is a bit of wiggle room in these things for getting, crossover between one signal to another and a range of one between another. Okay, so there is that as well, that there's sort of a wiggle room. However, in order for you to get the right signal, you have to have, like you see, all of this, once again, I've gone through this already, but you see it, all of the different number values that are on here, the height of the turns themselves, the height, the thickness, the diameter of the rod itself, the length of the rod overall, the length of the windings, right? There's a three-dimensional grid for you right there. All right, so it's extremely important to know this because of the fact that it is so difficult to get a good, clear signal of the Schumann resonances because there's a lot of moving parts. And 40,000 windings are a lot of moving parts. They literally wind it around and around and around and around 40,000 times. That's 40,000 moving parts just on that. Right? It's moved, and you have to get each one of them exactly right next to each other, and there's a certain pattern, a certain groove that it fits into, and if it doesn't do that, it's going to give you a screwy signal. Okay, there's a lot of precision that has to go into making one of these so that you can get a good reading of the meters. Okay, so this one here, we're going to see what this says. Oh, lovely. All right. So you can see for yourself the values that are given. I'll just let this sit up here for a little while. mm is obviously millimeter. So they're giving you the values that they used. Length of the ferromagnetic core is 300 millimeters. The diameter core, 25 millimeters. Diameter of the wire is 0.25 millimeters. The winding, the length of the coil, 250 millimeters. Thickness of the coil winding, 11 millimeters. So that's 11 millimeters of wires that have been wound up. They're starting at, 0.25 of a millimeter, and you have, there's now 11 millimeters. So that's a pretty substantial mass of wire. Come on. Diameter of the induction coil is 47 millimeters. The number of turns is 40,000. The value, the magnetic permeability variance is 66 there, if I understand that correctly. And the weight is 22.2 kilograms. So that's like, it's not that heavy, but it's noticeable, it's significant. All right. Okay, back to the material. The self-inductance, resistance, and capacitance of the single induction coil were firstly computed through the calculated value of the demagnetization factor, as well as the value of other geometry parameters and core material characteristics. Using Nagaoka, hopefully I didn't butcher that name too badly, Nagaoka's formula in the case of air coil inductor and a correlation factor lambda, I think, which is proposed by Lukos Chus, if that's the name. Reference 24, either way. For core material inductors, the magnetic antenna, self-inductance was calculated. Oh my God. Reference 25 and 26. The induction coil resistance was then calculated through 27. Reference 27. The magnetic antenna self-capacitance exhibited a strong dependence on the geometry of the coil as well as the wire insulator electric permittivity, that means permitting something, and the shielding that may be used between the coil layers. Okay, that's something that is important to note. I haven't exactly mentioned this before, but that's a point that is coming out. He's talking about the shielding. All right, this right here. This is really important to understand. Okay, so all of this, the self-capacitance exhibited a strong dependence on the geometry of the coil. So that means the self-capacitance is what the coil itself will hold from the ambient environment, if I'm understanding correctly, what its at-rest state is. I think that's the best way to put it. All right. The coil, and all right, on the wire, and there it is, and the shielding that may be used between the coil layers. All right. So in between the coil, the layers of the coil, I'm going to show you once again. There you go. That's a money shot right there. That's the picture of the magnetic coil, so you can understand what's going on. So all of this copper-colored stuff, that's the wire on it, and in between each layer, you wind it around. That's one winding. Where it goes all the way across, it is one winding. Okay. So they gave us the length of this. He gave us the length of this. Oh, good God. I should know. Oh, I think it's 2 meters, I think. Is that it? I forget what the length of the coil is. I should know this by now. All right. So it doesn't, maybe I shouldn't know this because I don't know if I've actually seen where it's written there. The length of the coil itself. Okay. So the length of the coil itself, I want to say this because we have talked about windings, and it's important to understand this. The winding goes all the way across once. All right, so this picture here is 2 magnetic induction coils back to back, okay? Let's just understand that there's 2 here. When we're talking about one, the single, which is aligned in either north to south or east to west orientation. Usually the antennas are back to back, but one's north to south, the other is east to west. That's usually how they do this. Okay, so the winding... All right, I guess it's 60 centimeter induction coil antenna. I think that's what we're looking at. All right. So the winding of it, it's turning, right? It turns all the way one layer, right? One layer is a turn. Okay. A winding is where you go all the way across once and then you start again. All right, in fact, I think you start at this end and then go back the other way, if I'm not mistaken. So you wind it this way, then you wind it that way, then you wind it this way, and then back that way. And so you keep going back and forth, and that helps to actually kind of, when you wind it one way and then you go back the other way, it helps to cancel out the field that's going out this way, right? And all the windings, you have the amplitude goes straight and the magnetics go out that way. So when you have a winding like that, it all wants to go in one direction, go one direction, go one direction, and you will build up successively a field of intensity as it keeps going around the coil. It keeps increasing, going around, 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 around. If it keeps going in one direction, that will increase the... I think it increases the amplitude. If you do it in a coil, it keeps going around. It's like a race. So if it's all going the same direction, let's say counterclockwise, it's all going the same direction, winding and winding and winding, it just increases the frequency, right? It just keeps going faster and faster and faster and faster as it goes around that coil. So what you need to do is stop its acceleration. So you go clockwise, get to the end of it, put a magnetically isolating shielding in between, then you start the next winding, layer 2. Over that magnetic shielding, and you go the other way. So the first way you wind it counterclockwise. Going back, you would wind it counterclockwise to cancel out the force, the inherent inimical, I think that's the word, inherent imminent force of that that process. So you want to cancel out the two. You cancel out the direction of the winding so that it allows for the two of them to cancel each other out. Okay, I think that's the simplest way to put it. All right, so so I want to point that out: the shielding, the winding, the shielding, the turnings. That's one of the important things. Also, for the purpose of computing such a parameter, several extended computations, reference 25, were needed. In practice, the induction coil self-capacitance was measured experimentally. Both calculated and measured values of the magnetic antenna self-inductance, resistance, and capacitance were summarized in Table 2. Well, that is a mouthful, isn't it? Okay. So but these are all the inductance, the resistance, and the capacitance. Three important elements, the parameters to setting up the antenna. The inductance is what it can transfer from the atmosphere into an electric signal. That's inductance. As it pulls that signal in, sends it as an electric impulse. The resistance is the natural stop. The impedance. The resistance is the impedance. It stops. To impede someone's forward progress is to stop them. Like when you're driving down the road and the police stops you, that's impedance. Your way has been impeded by the law. Okay. And the capacitance is basically what it can hold, like a sponge. If you think of it like a sponge or a drum that holds it, it's sort of, the capacitance is sort of like a battery. And a battery works in a little different way, but the battery is, if you look at it this way, from the basic standpoint, the capacitance is what it can hold relative to its volume, like a sponge or a drum. These are all great analogies. Okay. So Table 2, let's look at what Table 2 says. All right, so you see these values here. L is resistance. That's at calculated value of 23. I'm not sure what that means. The measured value is 249 Henry. All right, so the calculated value, this is what, according to what their figures say, what the math says, they should have an inductance of 233 Henries. Okay, so what they actually got is 249 Henries. So I'm not sure if that's better or worse for what they're doing, but it's a little difference. You see, it's a relative to there, it's a notable difference. Okay, so this was what they figured out in the equation. This was what it was measured at. All right, the resistance are, you see this, the calculated value, their numbers said they should have an impedance of 1,548 ohms, and they got 1,560 ohms. Okay, and the capacitance, which is what it can hold, that's they didn't calculate a value, or they don't show a calculated value, but they're showing 440 picofarads. And F is a farad, P is a pico. Okay, so that's what it's holding in its 440 picofarads of capacitance. Okay, so those are the three axes, if you will. Okay. Alrighty. Alrighty, where are we? All right. Okay. All right. I'm near the end of it. All right. That's why. Okay. Alrighty. The main resonant frequency. I was looking over on the right-hand side. All right. Let me get out of here. I was looking on the right-hand side for where I was, and I'm almost at the end of this. All right. So back to the literature. Okay. The main frequency. There we go. The main resonance. All right. Back on track. The main self-resonance frequency, which is 1 over the square root of the L and C, is the inductance and capacitance, I believe, of the single induction coil is 480 hertz. Okay, let me read that again. The main self-resonance frequency, which is 1 over the square root of L and C, of this single induction coil is 480 hertz. However, as the bandwidth of the Schumann resonance frequency component lies in the ELF range, there is no risk of degradation on our induction coil's performance due to these self-resonances, which are also filtered efficiently through our filtering and amplification stages. Sorry, not chain. All right. So I want to make sure to point this out. All right. You may not know what's important here, but let me just kind of tell you this. All right. I'm trying to get myself out of here. Okay. So, so they're talking about the resonance. There's the resonance frequency, the self-resonance frequency is 480 hertz, which is outside of the range of the Schumann resonances, first and foremost. Okay. But you're seeing here, 480 hertz, that is what this coil wants to naturally resonate at. So it's already vibrating at that 480 hertz signal. So, unless they filtered it out, what would happen is that when they put this on the scope and they looked at it up there, you would see a resonance, you would see a signal at 480 hertz. And it's extremely important to realize that this equipment operates at its own frequency. And it kicks up dust like pig pen. It has a difficult time getting out of its own way because it just is. It takes up space. It occupies space. It takes up matter. So the thing resonates at its own frequency. This one, the other one, all of them operate at their own resonant frequency. They need to be filtered out. And so that frequency, with the right conditions, can be amplified. If it's not filtered out, it'll show through. And even if it is filtered out, you can get multiples, you can get partials of the 480 hertz resonance frequency. And I need to say, this is why some of those antennas pick up these artifacts, because they're not filtered enough, but because what they need to filter out is the machine itself giving you a signal. All right, so what they're telling you here is that the bandwidth of the Schumann resonance frequencies lies in the ELF range, the low, 0.3 to approximately 46 hertz. There's no risk of degradation in our induction coil's performance. Okay. Yeah. All right, so they're telling you also filtered efficiently through our filtering and amplification chain stages. That means that those amplifiers and filters are extremely important for getting the correct signal out of the antenna. If it's not filtered, this is really important. If it's not filtered, you get input from the environment that shows up as some mark, some line, some artifact that later on will get observed by someone out there, you watching this, and someone seeing that will ask, what's going on with the world? They don't understand that the resonance of the antenna itself needs to be dampened, number one, dampened, and then filtered out. And you cannot, there's not a way that you can eliminate that entirely. It is. What you do is you filter it out on the back end of it. Okay. The implemented detection system includes two back-to-back coils. This is figure 2, I'm sorry, we see this below, right, resulting in the total coil length of 60 centimeters. Okay, so there we go. So each one of these coils is 30 centimeters long, and you have two that equal 60 centimeters. The housing of the induction coil antenna is provided by a plexiglass container offering a versatile and portable setup for easy transportation and installation and protection. The 60 centimeter induction coil antenna inside the plexiglass container is depicted in figure 2. All right, so that's this right here. Okay? All right. Okay. So this is a great picture of our magnetic induction antenna. Okay. All right. Where am I? The magnetic induction antenna. Our magnetic field antenna consists of two identical back-to-back induction coils with Mumetal core material. In order to achieve core alignment and excellent connection between the two induction coils, we used a clamp of Mumetal sheet. Our antenna output terminals are connected to the preamplifier inputs. A plexiglass box is used to protect the antenna and amplifier stage, mainly from moisture and humidity, providing also portability and stability. Through 3 SMA connectors, the preamplifier output as well as its positive and negative power supply is accessible. Right, so you see the little clamps there, right there. Okay, and that right there is a great visual of what a magnetic induction coil looks like. Okay. All right. Okay, so that will looks like that successfully ends our in this article our examination of the magnetic induction coil. So I'm going to end this video right now. Thank you all very much. I appreciate your support. Like, share, comment, and subscribe. And if you haven't already, hit the little notification bell next to the subscribe. And if you haven't already, hit the subscribe button. And periodically check to make sure you are still subscribed with your favorite channels. It's not just me, but all the favorite channels that you enjoy, that you like. YouTube does some funny things with the subscribers. So just physically go back. Don't depend on them. Go back and actually look at your channels like once a day. You know, at least go to your favorites and kind of see what they're up to. They may have posted videos that you didn't know about. Okay, so on that cheery note, thank you all for being here. I appreciate the love, the comment, and the support. Do comment. I like the comments from people. I like reading what people have to say. I may not reply to everything, but if you ask me a comment, I'm going to respond to it. And if I've read the comment, I just put a little heart next to it to let you know I appreciate the comment and the support. All right, so at that point, I think I'm going to end this video. It's been a long, wonderful trip for this one, but we're at the port of disembarkment now, so we have to... so it's time to move on. All right, so the next video here and the next part of this series will be the signal amplification chain. Okay, and I think that would be a great place for people to understand how these signals have to get filtered in order for there to be a good, solid signal. All right. Okay, so on that cheery note, thank you all for being here. I appreciate the support. Like, share, subscribe. I know I said that already, but please do it. And on that cheery note, namaste, and I will see you at the next video, which will be coming up soon. All right. So thank you all very much. I appreciate your being here. Have a great and wonderful day. Namaste.